One topic people have requested that I make a video about is worked examples in geometric algebra. I haven't really wanted to make this video until now since I generally work with theoretical math more than applied math, but over the years I have applied geometric algebra in many situations, and without even trying I have built up quite an assortment of examples. So in this video, I will work through several problems that I have run into in my own life, both in work and in leisure. A few notes are in order before we move on to looking at these problems. First, since these are all problems I have run into in my own life, almost all of them relate to what I do, making videos. In making the animations for my videos, I have had to solve many problems in computational geometry. Thus, most of these problems are in that vein. People working in other areas of math, physics, or engineering would run into very different problems than the ones I am showing here. I want to emphasize the practical utility of geometric algebra, so I am restricting myself to only problems I myself have run into. If you wanted to see some of the many other applications of geometric algebra in other fields, I'm sorry, but that's not what you're going to get here. But if your goal is to try to understand geometric algebra in general through some examples, I think this video will help. Another important thing to note is that most of the problems I will be presenting here are best solved using projective geometric algebra, also known as PGA. Different kinds of problems tend to require different kinds of geometric algebra, and for computational geometry, PGA is often the best tool to use. I've made a video about PGA that you can watch to get caught up on the topic. Finally, despite this video being about worked examples, I won't be including any numerical calculations. There are two reasons for this. First, including them messes with the flow of the video a decent amount, and it would take quite a bit of time as well. Second, and more importantly, we really shouldn't ever be doing these numerical calculations anyway. At the point that you actually want to calculate something, you should just use a computer to get the result. Geometric algebra gives us the tools to do geometry while completely forgetting about the details of the calculations. In fact, I haven't ever done any of the calculations involved in the solutions to these problems myself. So really, the lack of calculations in this video is the result of one of the strengths of geometric algebra, and it is not a weakness of the video at all. Anyway, let's get started. In this video, we will look at and solve 6 different problems. But what's that last problem? You'll have to wait until the end to find out. The first problem we will look at is determining if a polygon is convex or concave. Why would this be useful? To draw an arbitrary polygon, I have to split it into triangles. This process is called triangulation. Triangulation is practically trivial for convex polygons, but it is much more difficult for concave polygons. Thus, it can be helpful to have a way to determine if a polygon is convex or concave. So consider two polygons, one convex and the other concave. How can we differentiate between the two? The standard definition of a concave polygon is that there exists a line segment between 2 points in the polygon that passes outside the polygon, but I want to focus on another characterization of concave polygons. Notice that if we start at some point on the outside of a convex polygon and go around, we will always turn the same way at each vertex. Here, we are always turning left. But in a concave polygon, we sometimes turn left and sometimes turn right. We can use this property to determine whether or not a polygon is convex or concave. How do we determine what direction we are turning while going around a polygon? With geometric algebra. Consider two of the edges on the outside of a polygon. We can consider them to be vectors. Then the outer product of the two vectors will be positive if we are turning to the left or negative if we are turning to the right. We can just go along the outside of the polygon and calculate the outer product of each of these vectors, and then if at any point we get a different sign than before, we can stop and know that the polygon is concave. If we get to the end and all signs are the same, we know that the polygon is convex. The next problem that we will be looking at is finding the area of an arbitrary polygon. So consider an arbitrary polygon. How can we find its area? Well, one thing we could do is form all the triangles between the origin and all the vertices of the polygon. The area of the polygon is the sum of the areas of the triangles. How do we calculate these areas? With geometric algebra. Let's label the vertices of the polygon. We can interpret the vertices as vectors from the origin. Then, the outer product of two adjacent vectors produces a bivector that represents the parallelogram made by the two vectors. This parallelogram has twice the area of the triangle the two vectors make, so we can divide by 2 to get a bivector representing that triangle. We can repeat this process for all pairs of adjacent vertices, and then add them together to get a bivector that represents the whole polygon. We can factor out the 1/2 here as well to make it a bit simpler. Then, the area of the polygon is just the magnitude of this bivector. In 2 dimensions, bivectors only have one component, so this is as simple as reading the coefficient of E12. Now there are several seeming issues with this procedure, but they end up not being a problem at all. The first thing is that it seems like this only works on convex polygons with the origin on the inside of them. For example, let's say the origin was over here instead. Then it seems like this procedure would start including areas outside of the polygon. But remember, bivectors are oriented. Notice that when the origin is on the outside, some of these bivectors are clockwise, while others are counterclockwise. In fact, the clockwise bivectors don't even go into the polygon at all, and they end up getting exactly cancelled by the parts of the counterclockwise bivectors that aren't in the polygon as well. When adding all the bivectors together, all parts outside of the polygon end up cancelling, and the final result is still the bivector representing the polygon, even though the origin was on the outside. So we see that the position of the origin doesn't matter at all when calculating area like this. For similar reasons, this algorithm works with concave polygons as well. Even though some of the bivector parts end up including regions that are outside of the polygon, they always cancel with other bivectors. In general, no matter what the polygon looks like and where the origin is, this same formula works to produce the area. Now, one strange thing that can happen is that sometimes, when using this algorithm, the results can be negative. Let's go back to the convex example we were looking at earlier. If we had reversed the order of all the points, the bivector the formula produces would have a negative E12 component. But we can't have a negative area. Well, we can solve this by just taking the absolute value. The absolute value of the E12 component will always be positive, and it will be the area of the polygon. But what exactly makes one case produce a positive value and the other case produce a negative value? Notice that in the first case, our points were going along the outside of the polygon counterclockwise. But in the second case, our points were going clockwise. The order of the points along the outside ends up being the orientation of the bivector we get representing the polygon. So the sign we get with this algorithm does have significance. It represents the direction the points go around the polygon. Interestingly, this is the main reason I have used this algorithm. I've never really needed to find the area of a polygon personally, but there are many other algorithms, such as polygon triangulation, where it's important to know whether your points are going clockwise or counterclockwise. Even though I've never needed the area, this is the simplest algorithm I know for determining the winding order of a polygon, so I have used it whenever I needed to figure that out. The next problem that we will look at is non-uniform scaling. This is the part of the video where everything from now on will use PGA. Again, I've made a video introducing PGA, so you can watch that if you need to. I'll assume you know the basics of how it works at this point. Anyway, non-uniform scaling. To talk about non-uniform scaling, let's first talk about uniform scaling. Uniform scaling is the well-known operation where you take all points in space and scale them all by the same amount around the origin. Non-uniform scaling is when the amount that components get scaled depends on the direction. For example, here we are scaling the x component while leaving the y component alone. In my video that involves multiplying vectors and bivectors, I wanted to use non-uniform scaling on bivectors to graphically represent the contractions that happen when doing these multiplications. This is an operation that is a bit notorious among people that do geometric algebra because most say it can't be done without falling back to matrix-based methods. So how do we do non-uniform scaling if we can't use geometric algebra? We use geometric algebra. Let's think of this case a little more, where we scale the x component while leaving the y component alone. In general, we are scaling a point P in a direction D from a point A. We will represent the direction D as a point at infinity in the direction we are scaling. The fundamental idea here is to notice that when considering just this point P, non-uniform scaling along the x-axis from A is the same thing as uniform scaling from this point right here. We just need to find an expression for that point and we should be good to go. To find that point, we just need to do a few PGA calculations. We can get the line we are scaling along by joining the point A with the direction D. Then, multiplying this by the point A, we get this line. Something interesting about this line is that it is unchanged by the non-uniform scale. In a sense, it is the axis of scaling. Let's call it L. Then, we can get the point that will correctly scale P by projecting P onto L. Like I just said, we can do a uniform scale from this projected point to perform the non-uniform scale on P. To do this non-uniform scaling for other points, we just have to repeat the process. However, the line L is the same for all points, so we only need to calculate it once. The only thing we have to calculate for each point is the projection of that point onto L and the uniform scale itself, which is pretty simple. The line L seems to be more fundamental to this process than we initially thought. Instead of specifying a point A and direction D to scale with, we could instead just specify this line L. In higher dimensions, this process generalizes very nicely. In 3 dimensions, using our original conception of the problem with a point A and direction D, the same process ends up producing a plane that we scale around rather than a line. Again, instead of specifying A and D, we could start with just this plane. In fact, we could pick a line to be the axis as well. So the final way we can describe this process is this. Given an arbitrary object in space like a line or a plane, we can do a non-uniform scale around it by taking each point, projecting it onto the object, and then for each point, doing a uniform scale from that projection. This produces a non-uniform scale that doesn't affect that initial object. The next problem is how to draw planes. Back when I was working on my PGA video, I needed a way to draw planes. Planes are infinite, so you can't really draw a full plane, so what I really needed was a way to take a plane and then draw a segment of the plane in 3D space. In particular, to actually draw this plane segment, I needed to find the vertices of this shape. One issue that we run into is that there are actually many different plane segments we could pick. So we have to add a few constraints onto the problem to deal with this. First, I decided to make the center of the plane segment be the point on the plane that is closest to the origin. This would keep things on the screen as much as possible. But we still have a rotational degree of freedom here. To fix this, I decided that one direction, such as the z-axis, is the up direction, and I wanted to align the plane with that direction. One issue here is that if we have a plane that is perpendicular to our up direction, the plane can't really be aligned with that up direction. In this case, we can just pick a different up direction, such as the y-axis. With all of these constraints, how do we draw a plane? With geometric algebra. Let's call the plane P and the origin O. Then the inner product of P and O is the perpendicular line passing through the origin. Let's call it the axis, or A. Let's also call the point on the plane that the axis passes through the center. We can then project a point in the up direction onto the plane. If this happens to be equal to the center, we would have to pick a different up direction. Once we have a valid up direction, we can join this projected point U' with the axis to get this perpendicular plane which we'll call P1. We can also take this plane and multiply it by the axis to get this other perpendicular plane which we'll call P2. We can normalize these two perpendicular planes and then add and subtract a particular multiple of E0 from each of them, shifting them away from the center by that scalar multiple. Then the 4 vertices of the plane segment we are trying to draw are the intersection points of some of these planes. The next problem is how to draw curves. Here's what I mean by that. Consider some random mathematical function. How would you draw it on the screen? You might think that you can just calculate the result of the function at several points and then draw a line between each point. However, this is more complicated than it might seem since the curve itself needs a bit of thickness to look good. If we just drew a bunch of separate lines between points and gave each line a bit of thickness, we would have little gaps near each of the points. So how do we fix this problem? With geometric algebra. Let's label all the points we have here. We can calculate the lines going through each pair of adjacent points by calculating the join of the points. To give the curve a bit of thickness, we can shift each line a bit in both of the directions that are perpendicular to it, which can be done by adding and subtracting a scalar multiple of e0 to the lines. Then we can calculate these intersection points between adjacent lines. If we draw the curve based on these intersection points, we won't have the gaps we had before. By increasing the number of points we sample and by making the curve a little thinner, this algorithm can produce results that look quite good. There are a few kinks involving collinear points that I had to work out, but solving those kinks is too big of a distraction here. And now, the moment you've all been waiting for. The final application of geometric algebra we will be looking at is getting better at Minecraft. In my free time, I sometimes like to casually speedrun Minecraft. I recently set a goal to beat the game in under an hour. But no matter what I did, I couldn't quite get it. I started foregoing materials before going to the Nether, I was learning bastion layouts, and I even learned how to use the pie chart. But none of these things helped. But you know what did help? Geometric algebra. One of the things you have to do to beat Minecraft is find what's called a stronghold. To find it, you have to use an item called an Eye of Ender, which will fly in the direction of the nearest stronghold. The strat that people usually do to find a stronghold is to use an eye, follow it for a while, then use another one, follow that for a while, and repeat until the eye goes underground, at which point you are right above the stronghold. There are two main issues with this approach. First, it's pretty slow since you often have to travel pretty far to get to the stronghold. Second, Eyes of Ender are very difficult to obtain, and it's possible to lose them in this process. However, there's a better way to find the location of a stronghold. Let's say this is the position of the player, and this is the position of the stronghold. After using one eye, you know that the stronghold will be somewhere along this line. Instead of following the line, you can move perpendicular to it and then use another eye. This produces a slightly different line that the stronghold is on. You can then calculate the precise location of the stronghold by finding the intersection point of these two lines. So how does this work in practice? Here's the general strategy that I ended up using. First, after throwing an eye, I turned my FOV and mouse sensitivity all the way down and looked directly at the center of the eye. By doing this, the direction I am facing is precisely the direction that the eye is going in. Then, I pressed F3 plus C, which copies your coordinates and your facing angle to the clipboard in this form. This is the X coordinate, this is the Z coordinate, which we'll think of as a Y coordinate, and this is the facing angle in degrees, which starts at 0 in the positive Z direction and then increases as you turn towards the negative X direction. We can then convert the coordinates to a 2D PGA point. For the facing angle, we can find a point at infinity in that direction by using that angle in a rotor. The coordinate system of Minecraft is a bit funky, but here's what you actually have to calculate. Then, taking the join of the point you are standing on and this point at infinity, we get the line the stronghold is on. Moving a bit perpendicular to this line, I threw another eye and repeated the process. After getting these two lines, we can just calculate their meet to get the position of the stronghold. When I first did this, I went back into the Nether and traveled to the exact coordinates that I calculated and built a different portal there, because traveling in the Nether is 8 times faster than traveling in the overworld. The calculation was precise enough that the portal dumped me directly inside the stronghold, at which point the rest of the game was relatively uneventful. Did I finally get a time under an hour? The time ended up being 49 minutes. Okay, I'll admit, I think part of this was due to the Nether being easy to travel in this world, but still, traveling to the stronghold in the normal way takes forever, and I'm sure that removing most of that time was a huge part in getting a time that good. Before I finish here, I want to say that yes, I do know that speedrunners already triangulate the position of the stronghold without using geometric algebra. And I'll admit that it was knowing that they already do this that gave me the idea. But I think it's still valid to show this here as an example application of geometric algebra for two reasons. First, the calculations for this process are much simpler using geometric algebra. How many speedrunners can actually do these calculations themselves without looking anything up? Geometric algebra is simple enough that I easily derived these equations myself, and it would have been much harder to do without geometric algebra. Second, we actually get a bit more information out of this algorithm than the intersection point. No matter how hard you try, it's very difficult to get the exact angle that the Eye of Ender flies. So there's often a bit of uncertainty in the angle of these lines. For an algorithm like this, where we are finding the intersection point of two almost parallel lines, this small bit of uncertainty can make a huge difference. When doing the calculations in PGA, this uncertainty actually shows up in the equations. After calculating the meet of the two lines, we have to normalize the resulting bivector to be able to extract the coordinates of the stronghold. It turns out that the E12 coefficient, which is the number we need to divide by to do this, is related to the uncertainty. It will be 0 when the lines are fully parallel, and it will be 1 when the lines are completely perpendicular, as long as you normalize the lines first. So you can look at what value that is to get a feel for how precise the coordinates of the stronghold are. I even change my strategy depending on the uncertainty. If that coefficient is high enough, I'll build my portal in the ground hoping to appear right inside the stronghold. But if the coefficient is too low, I'll try to build my portal so that it appears on the surface, where I can throw 1 or 2 more eyes to nail down the stronghold's position even further. So the geometric algebra solution actually added something over other people's solutions. We have now looked at all of the problems I wanted to cover in this video. And just to be clear, there are many more situations where I have used geometric algebra. I was going to include some of these in this video, but I removed them mostly for the sake of time. Maybe I'll make other videos covering some of these topics at some point. Anyway, I hope that this video has helped you learn both how useful geometric algebra can be and how it's actually used in practice.